When we look up at the night sky, why do some stars appear to be brighter and some stars appear to be fainter? Well, some of these stars are really, really close to us and some are really far away. Some stars are just a little bit more luminous and some stars are not as luminous. It is a combination of the luminosity of a star, how much energy it emits per unit time, and the distance that a star is away from us that determines how bright it will appear in our night sky. So let's imagine that these two light bulbs are stars. Let's imagine that both of these stars have the same luminosity. If one of these stars is closer to us and the other star is further away from us, the star that is closer to us will appear to be brighter. Now, let's say that both of these stars are the same distance away from the Earth, but one of them happens to be more luminous than the other. And the star that's more luminous will definitely be the star that appears to be the brightest in our sky. The brightness of a star is given by this equation right here. The brightness of a star is equal to its luminosity divided by 4 pi times d squared. In this case, d is the distance between us and a distant star. So the luminosity is a quantity that describes the amount of energy that a star emits per unit time. And the unit of luminosity is units of watts, just like wattage on a light bulb. And so the unit for brightness is actually going to be a watt per a distance squared, so a watt per meter squared. And here this 4 pi d squared, what does that represent? This 4 pi d squared represents the surface area of a sphere. So in order to calculate the brightness, we're looking for a luminosity per unit area. And that unit area is going to be the surface area of a sphere that's centered around our star. As the light from a star travels a further distance, that light must spread out over a larger surface area. And I'll show you what I mean by that here. So imagine we have our star here, and around that star we have a sphere that's centered on the star. Okay? And that sphere I'm representing here by this circle centered on the star. And the radius of the sphere would be the distance between the center of the star and the edge of the sphere here. And so that star's luminosity, its energy per unit time that it's emitting, is spread out over the surface area of a sphere. And the surface area of a sphere is 4 pi times the radius of that sphere squared, or the distance that we are away from that star squared. Okay? And as you move out a further distance, let's say we have a bigger circle or a bigger sphere that's centered around our sun here. As we move out a further distance, that d in this equation gets larger. That radius of this concentric sphere centered on the sun gets larger, and so then the brightness of the star will decrease as we get further away from the center of that star. So the further away you get away from a star, the less bright or the fainter it will be. The closer you get to a star, the brighter it will be. And it's all determined by this equation here. Now this equation is a form of an equation that we see a lot in physics, and it's called an inverse square law. And an inverse square law tells us that the brightness is inversely proportional to the distance between us and that star squared. We see these types of inverse square laws everywhere. We see them with the gravitational force between two bodies. We see it in electrostatic forces between two particles. We also see it when we're trying to calculate the intensity of sound, and here we're calculating quantities related to light. Let's consider two stars of the same luminosity in our sky, but one of them is twice as far away as the other star. So this equation tells us that that star that's further away is going to be 1/4 the brightness of that star that's closer to us. So you might think instinctually that if a star is twice as far away, it's going to be half as bright. But this inverse square law equation for the brightness of a star tells us that if a star is 2 times further away than another star, then its brightness is actually going to be related to 1/2 squared. And so 1/2 squared would be 1/4. And so that star would actually be 1/4 the brightness of our star that's closer to us. Suppose we have two stars, and they both have the same luminosity. But star 2 is twice as far away from us as star 1. And we want to figure out how much fainter is star 2 compared to star 1. And in order to do that, we are going to set up a ratio of the brightness of star 2 to the brightness of star 1. And so remember that our brightness we can write as the luminosity of the star divided by 4 pi d squared, which is the surface area of a sphere. So the subscripts here, 2 and 1 on both of these, just refer to the fact that this luminosity is for star 2, this distance is for star 2, okay? And also, I can also write the fact that since star 2 is twice as far away from us than star 1, we can say that d2, the distance to star 2, is equal to twice the distance to star 1. We'll be using that here in a minute. Now we have this fraction, and we have a fraction where on the top we have also a fraction, and on the bottom we have a fraction. And so when we divide by fractions, this is the same thing as multiplying by the reciprocal of the bottom fraction here. So I can rewrite this expression in the following way. I can say that the ratio of my brightnesses is equal to L2 divided by 4 pi d2 squared times the reciprocal of our bottom fraction times 4 pi d1 squared over L1. Okay, now since the luminosity of both of these stars are the same, then L2 is equal to L1, so I can cancel these out here. We've got 4 pi on the top and the bottom, so I can cancel those out here. And my resulting equation is just saying that B2, the brightness of star 2 over star 1, is equal to D1 squared over D2 squared. So it's equal to the distance to our first star squared divided by the distance to our second star squared. Now remember that I said that the distance to star 2 is twice the distance to star 1. So I can replace D2 with this expression right here. So down here I'm going to say that this is equal to D1 squared over 2 times D1, that entire piece, squared. Okay? Now, this is again equal to D1 squared divided by, so 2 raised to the power of 2, I'm going to put that there, and then times D1 squared. Okay? So we see that we've got D1 squared on the top, D1 squared on the bottom, so those cancel. So we're left with, finally, just 1 over 2 squared, which is 1 over 4, 1/4. And so this tells us that the ratio of the brightness to star 2 to star 1 is 1/4. So that means that star 2 is 1/4 times the brightness of star 1. Or you can also say that as star 2 being 4 times dimmer or fainter than star 1.